Hello, my name is Brett Champion, and my team works on all the plotting and charting functions in the Wolfram language. And today we're going to look at some new functionality for visualizing complex valued data and functions. So since the beginning, when Mathematica was originally released back in the late 80s, mathematical functions have been a key part of the system. Common functions like polynomials and basic trig functions, but also the so-called special functions like the Bessel family and hypergeometrics and more exotic things even. And a lot of effort has gone into being able to compute integrals, identities, find singularities for all these different types of functions. Even so far as to the point that several years ago we created a website called the Functions Mathematical Functions site that has sort of all the information that we've accumulated over the years about things. So, as a brief aside, if I look at elementary functions, say sine, and if we look at, so we have definitions and integral representations and all sorts of things. If we look at representations through equivalent functions, related functions, let's look at things involving cosine. Then you get sort of all kinds of interesting trig identities, including sort of halfway down the page, the one that everybody knows best, that sine squared plus cosine squared is equal to 1. And so a lot of efforts going into being able to work with mathematical functions and their full generality. And so, but when it came to plotting, sort of up till now, we've been mostly restricted to thinking of real valued functions over being plotted over real numbers. And it was possible to do complex valued things by sort of manually constructing them, using real numbers. But we wanted to make these more straightforward and have built-in functionality for that, because a lot of these functions are sort of really interesting, especially once you get off the real line and are looking at the full generality over the complex plane. And so now in version 12, we've introduced 5 new functions for visualizing complex valued data and functions. And we're going to take a look at those and then look at some applications of them and how to interpret and make use of them. So jumping into the new functions, the simplest one is complex list plot, and it is essentially list plot, if you're familiar with that, but for complex numbers. And so it takes a set of complex numbers, and I'm going to paste that real quick, and if we numericize it, then we see that we have a bunch of things that have real and imaginary components. And so this just plots the numbers in as points in the complex plane. And so this is built on top of our existing list plot. It has a little bit of additional functionality added into it. So in addition to looking at a Cartesian, real, and imaginary axis, we can also tell it to use polar axes, in which case we have the radius is the magnitude, the absolute value, and we look at from 0 to pi, or 0 to 2 pi, I guess, as the argument. And because it's a list plot, then it inherits sort of all of the normal list plot functionality, and we leverage everything in our toolbox for visualizing sets of points. So in this case, we're going to label each of the points with a call out, so that we can see what each of them is. And so that's sort of useful functionality. I mean, you could do it previously. You had to sort of manually apply re and m to your values. If you had, say, wrappers like callout or style or labeled or this sort of thing, it would have been a little bit trickier to perhaps to apply to extract the real and imaginary parts, sort of at the right place in a robust manner. So that part's all automated and easy to use now. So the next two functions are reimplot and absargplot, and these are looking at what happens when you have a function that goes complex valued when you're plotting over the real numbers. And so this is a fairly common experience that people have, that they plot something x to the 1/3 from -3 to 3, and they only get half of the plot that they're expecting. And then the reason for this is that sort of x to the 1/3 isn't the cube root that people are thinking of. So this is done via principal value, and so there's of course 3 solutions to y equals x cubed, if you solve for y or solve for x, and we plot one of them, sort of by default, and so we've introduced reimplot, which can be sort of useful in these cases, which plots the real and imaginary parts separately. And here we have an example of that for our x to the 1/3. And this is the real part as a solid line and the imaginary part as a dotted line. And so you can see for positive values of x, we have sort of an interesting real part, and the imaginary component is strictly 0, which corresponds with what plot was showing us. And then for negative values of x, we see that both the real and imaginary parts are non-trivial, that they both contribute to what's going on there. And we can use, we have a couple of options specifically for reimplot. So the ability to style the real and imaginary components, and the ability to control sort of what terminology is used for labeling the real and imaginary parts. So reim style and reim labels. And so coming back up to this sort of for a moment, and going into a little bit more depth. So, as I was saying, this is not what people are expecting to see. People are expecting to see cube root, which was added, I don't know, version 9-ish, maybe 8, 9, version 9. And so it helps if I give it a variable. And so this is the curve that people are expecting to see a lot. And I'm going to pull in a little bit of additional examples. So as I was saying, if we solve y cubed equals x, then we get 3 solutions. And if we go back to our complex list plot, what I'm going to do is generate a set of points for each of these solutions. So and plot them, and then we see that sort of these are our three sets of solutions. And if I join them, then this is the one that we get by default, the principal value. And so you can see that it's real valued along the positive x-axis, and then it goes complex sort of off along, in a particular direction for negative values of x. This one is sort of complex everywhere. And then this one is the other half of our cube root plot. And so it's just sort of interesting to see how that goes. And the fact that sort of these go off in constant angles is going to be relevant for the next section where we're looking at Ab's argplot. So Ab's argplot is very similar in some ways to reimplot in that we're plotting a complex valued function over the reals. But because the complex numbers have sort of this dual identity that we tend to think of them in, either a Cartesian real and imaginary part, or a more polar angle and radius sense, then we have functions that visualize both parts of that. And so here we have our third root of x again. And what this shows us that wasn't necessarily as clear from the reim plot. So let me go ahead and get a reim plot up for comparison. And so here you see the real and imaginary parts, but it's not necessarily easy to see what happens when you combine the real and imaginary parts. And so the Ab's argplot in this case allows us to see that the magnitudes are symmetric across, for the positive and negative values of x, which isn't sort of as clear from here. And so the height of this curve corresponds to the absolute value of our function, and the color corresponds to the argument. And so we have a legend here that shows it going from minus pi to pi in sort of a cyclic valued color function. And so the legend has all of these colors, but it doesn't have. But when you look at the plot, you don't necessarily see them. I mean, everything is just sort of two colors, which might be confusing for a little bit. But then you look at, say, this plot of where the numbers are, where our complex values are, and it makes sense. So we're looking at this branch cut, or this, not branch cut, this solution to the equation, this particular root. And we see that we have a red curve at 0, and we have a yellowish curve at pi over 3. And that corresponds to these. And so if I pick a different one of these solutions and feed it into Ab's argplot, then we get something that looks very similar in terms of how quickly things grow, because these are all sort of coming from the same function, but we get different colors. And so we get sort of a magenta-y purple, which is down here at minus pi over 3, and this bluish color, which is at minus 2 pi over 3.
But we get to
and those correspond to these two yellow rays going out from the origin. And if we were to plot the third solution, then you'd get three different colors yet again, or two different colors yet again, corresponding to these two directions. And so those are our first three complex valued visualization functions. And then we get to sort of the really fun ones, which are complex plot and complex plot 3D, which are plotting the magnitude and the angle, the argument, of the function over the entire complex plane. Well, not the entire complex plane. We bound it. In this case, we're going from -3 to 3 in the real and imaginary parts. And so, as with abs-arg plot, the argument is going to be represented by this color going from minus pi to pi, turquoise to turquoise with red in the middle. And for the absolute value, we have, by default, this sort of lightening of the color as it increases in magnitude. And then so as you approach infinity, you sort of get close to pure white. And down by 0, you get sort of the full saturated colors. So that's complex plot. Complex plot 3D is very similar. We use the same color function, but because it's a 3D plot, we don't have to do the shading, the secondary shading, to show what the change in height is, and so we just use height for the magnitude of the complex number. And so that's the basic idea behind complex plot and complex plot 3D. And so if we come back to our sort of main page, you'll see that we then have an entire row of examples that sort of walk us through how to interpret the complex plots, and especially complex plots. Because once you get sort of familiar with these, you start to be able to recognize what certain types of features look like. So, for example, and we're going to look at a series of examples that are sort of very simple functions that we know what the behavior of them is, and use that to identify what features look like. So we're starting off with z, simplest non-constant function that you can get. And so what you see is that we have, in this case, we go from turquoise through the purples to the reds, through the oranges and greens, and back to turquoise around a point in a counterclockwise manner. And that is what a 0 will always look like. It will always be going from bottom to top on this color function, or from min to max, in a counterclockwise manner. The details may vary. It may be that we start over here and go around and end up back over here, but it's always going to be that counterclockwise. On the other hand, for a pole, such as 1 over z, we have the same behavior but in a clockwise manner. And so sort of the fact that you've inverted, done 1 over 0 to get the pole, sort of reverses the sense of that. And if you have a multiple 0, so here we have z cubed, which has a 0 of order 3 at the origin, we're going to see the same behavior, but we're going to see it happen 3 times. And so we have our turquoise to turquoise to turquoise to turquoise 3 times around this point. So this is a 0 of order 3. Likewise, for a pole, you would have it going clockwise 3 times around a pole of order 3. So moving up into sort of more interesting types of singularities, if you have an essential singularity, then what is going to happen is you have an infinite cycling through the color function as you approach that point. And so, let's see, so we're going to start over here on the right in this case. And so we go turquoise to turquoise to turquoise to turquoise, 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 and then we start coming out the other side. And in the middle here, at the essential singularity, you get sort of that infinite cycling of your color function there, corresponding to the function taking on sort of an infinite number of values around that point. And just a second, I'm going to copy this one for a moment and go ahead and look at it with complex plot 3D as well. Okay. Because one of the things that I want to point out with the essential singularity is that you sort of have almost a 0 on one side, and then it blows up on the other, and so you can sort of see that as we're coming in, we're one side is staying very well behaved in terms of absolute value, and then the other side is sort of blowing up. The interesting thing there is that it isn't is that change in absolute value is happening sort of perpendicular to the direction of the color cycle. So we have this side, so the top half is where we get the function going to large value, positive infinity. Let's see. And so coming back onto some of the more discontinuous types of singularities that we can run into. So if you have, say, z to the 3 halves, then that looks like a 0, but it should have order 1.5, and that's actually sort of what you see. So we go from turquoise through to turquoise one time, and then we've got sort of a little bit extra that shows up, and so it really behaves like we saw for a 0 of order 3, even though it's a fractional power in this case. And the same thing for a pole, you get the same behavior but going the other way around. There's a thing that shouldn't have made it into the web page. Comment for the authors, I guess. Let's see. And so if we look at something more interesting like floor of Z, which converts our, sort of maps the continuous complex numbers into discrete, in this case, essentially the Gaussian integers, then we see that we end up with what you would expect, that we have sort of large blocks where everything is the same. And so that's sort of interesting. These two blocks, sort of look like they're the same, but it's just the color function doesn't distinguish between those necessarily well. There is actually, I believe, a small difference in those colors. And so, well, right. So, as I was saying, by default for complex plots, as the magnitude of the function gets larger, then it fades out to white at infinity. And so there's actually a lot of flexibility in that, in terms of what shading we use for the height or even for some of the other properties of the function. And so you may have noticed that, like say for this complex plot over here, it has color function set to none, which in this case means don't do the absolute value shading. Just show me the colors. And in general, complex plots color function takes a little bit. It has the ability to take a list of two things: a color and a height shading specification. And so I'm going to look at a few of the shading specifications that we have using this function z squared minus 8 over z. And so this has one pole at z equals 0 and 3 zeros distributed around the origin. The function looks like it only should have 2 zeros because there's z squared, but so if we do together of that, then we see that really that's a cubic in the numerator, and so that's why we have 3 zeros instead of 2. When we were working on this example, it took me a moment to figure out why the numbers weren't matching the way I initially thought they should. And so we have our 0. So this is our default shading function. So we have our pole at the origin, and then we've got our 3 zeros going from turquoise through orange, yellow, back to turquoise, turquoise through orange, turquoise through purple, orange, yellow, back to turquoise, turquoise coming around, all of those going counterclockwise, one time around. And this is a good demonstration of, so if they're all zeros, they all have that cycle going counterclockwise, but all of them sort of start at a different location. That is a result of sort of being influenced by each other and this pole in the center. And so by default, the shading isn't actually being done on a 0 to infinity scale. It's actually looking at sort of what the minimum and maximum values within that region are. And that works, reasonably well a lot of times. It's possible to say that you really do want it to be computed sort of globally. And what will happen is that this will tend to okay. Just a second. My headset turned off for a moment, so if Min or somebody can verify that they can hear me in chat, then we'll just double check that. Hello? Okay, you can hear me. Very good. So anyway, like I was saying, you can do a global scale where it really does go from 0 to infinity, and in this case, it's actually going to go even before, beyond full saturation, where we're going to end up with little black dots effectively at each of the zeros and full white at our poles. And so that can make it sometimes a little bit easier to identify zeros because you don't necessarily have to check quite as carefully what direction the colors are going. So this is based on the quantiles of values that you see. So that, I forget what the exact number is, but say you start going to your really dark black shading for the bottom tenth and your really white shading for the top tenth of the values. And so you get sort of the blacks and the whites for the zeros and the poles without washing out the intermediate colors quite so much compared to this one or that one. And then we get into sort of the really crazy shadings. And so what this one is doing is the colors. I mean, so for all of these, the colors are sort of the same. And it's just additional shading happening on the colors. And so we have a log scale where every time the magnitude changes effectively by about a factor of 2, it's going to go from light to dark. And so then you can see light to dark, light to dark. We have sort of increasing values as we come in toward our pole. We have dark to light as we come into our zeros and decreasing into them. And occasionally this can help to let you see at what rate things are changing a little bit better than a small change in color gradation might do somewhere else. This one is a little bit similar. It's doing a lot of the same cyclic log abs, as cyclic behavior as log abs. The difference is that it's sort of shifted. I mean, the log scale is shifted a little bit in a way so that 0 is always the full color. So it has sort of a one-ended log scale. And so you end up with, let's see, if I do this over here, then I can make it a little bit bigger, and it helps if I define F. And so you end up with a little color wheel at the center of each of your zeros. And then you have your sort of light to dark transitions as it grows out. And when you go into a pole, you won't end up with the same color wheel because you'll get sort of the accumulation of this banding coming up on that point. And so it ends up looking a little bit differently. So most of the ones we've looked at so far have done the shading based only on the magnitude of the function. But it's possible to do the shading based on other things in cases where it may be desirable. So in this case, we're doing the sort of same cyclic behavior, except that we're doing it for the argument. So we're doing it in addition to our main color function. In this case, it doesn't need to be on a log scale because we know that the argument is bounded between minus pi and pi, and our color function goes sort of uniformly through that. And so this allows you to see perhaps a little bit more clearly where you have relatively constant values of argument, because this is essentially going to create, I mean, the bands serve to work almost like contours or mesh lines in this case. In this case, we have cyclic log abs arg, which is doing sort of double shading in the abs and the arg. And so you can see the arg contours as well as, so it's a sort of blending of this one and that one. And then finally, we have one that is doing a log scaling to get these sort of white bands according to the absolute value. And then we have the real and imaginary parts are being done as a dark banding, similar to this one. And so you can see where you have your real and imaginary contours, essentially, in addition to through the dark curves that become sort of apparent. And so then we have sort of everything changing all at once practically. We have our real and imaginary parts being represented. We have our magnitude and abs being represented, and we have our argument being representative. I don't claim that you can necessarily that you'll necessarily look at this and immediately decipher everything that's going on, but it's sort of the maximal use of that space, and so as you increase the complexity in a plot, it tends to increase the amount of effort that it takes to understand and extract all the nitty-gritty details. So in addition to sort of using the shading to get contours or mesh levels, you can of course use meshes in the normal way. And so in this case, we have our slightly different function. It has just 3 zeros, no poles. And we can look at the real and imaginary parts of that function. So slot 2 corresponds to this. Slot 1 is Z, so your domain. And I've made the real mesh lines black and the imaginary ones white. And so everywhere along a black curve, you would have the same real component and same imaginary component along a white curve. And so here's a slightly more, all right, so this is showing the mesh lines for the magnitude and the argument, and so you can see that the argument is the white lines, and they basically have the same color everywhere that a particular line goes. And so saddle points are typically going to show up at sort of where you have. Well, I mean, you can see that there's a saddle point because these mesh lines sort of start to diverge from each other. They don't really want to cross here. But you can also sort of see that in that we have sort of yellow, and red sort of across from each other. And it's the same with the blues and the greens happening at this saddle point. They show up really well on the complex plot 3D. And I'll just sort of point out that this complex plot 3D is using a log scaling function which is sort of really useful sometimes, because what it will tend to do if you set a log scaling function is if we have, say, z minus 1 plus 1 over z plus 1, z goes from minus 2i to 2 plus 2i. Um, oh, I just want that divided. I don't want. Okay, right. So we have a 0 at 1, and we have a pole at minus 1. And it can be a little bit hard sometimes to see that 0. But what will happen is if you set scaling functions goes to log, then that tends to sort of bring the 0 and the pole onto a symmetric scale. And so then we see the 0, sort of really points down, and the pole really points up. And so using a complex plot 3D with scaling function goes to log can sometimes really accentuate those zeros, while at the same time taming the poles a little bit. And so that works really well a lot of times, and I like to use that. And so, the end result of this is that, after you've worked with these a little bit, then you can just do the plot and start picking off features. So here we have a rational function, and I can see, okay, there's 3 zeros here and 4 poles. Here's a ratio of a couple of gammas raised to powers. And so we've got a string of poles along the top here and a string of zeros along the bottom here. And the zeros are sort of all order 2. Sorry, the zeros are order. Yeah, zeros of order 2. So green and green, green and green. And the poles are order 3 because we've got sort of our 3 reds going up around here. Really easy to see how many, what the order is of something. And then we have this function. We had a lot of fun trying crazy combinations of functions to see what they looked like while we were working on this. And so we have cosecant of 5 pi over z cubed minus 1. I mean, the 5 pi doesn't really contribute anything. It just changes some of the scaling a bit. And so you get this sort of really interesting looking plot. And so we have some poles coming off on these diagonals, or on these, in 3 different directions. We have poles that are accumulating into essential points at 3 different places. There's no zeros. And then we have sort of this big pole at the origin. And so it's just really interesting to see sort of what things look like. And as I was saying, I can look at this and pull. I can see all the poles. I can see the essential singularities. If I take time to count, I can see that these are all poles of order 1. Along these. And so just being able to sort of see what the behaviors are at a glance and sort of identify what the patterns are is sort of really really fun and interesting, I think. So let me see. So that's there. I'm going to pop back out to the main page. Um, and so, um, right. So that was our mesh example. Okay. Um, let's see. So don't think we have any questions yet. Okay, wait, there's manipulate. Do I want to know what this manipulate does? Okay, I'm curious. We have a definition for f. This definition for f looks familiar. Okay, fine. Oh yeah, this. We'll get to some examples like this pretty soon. And so one thing that I wanted to mention is that, so sort of if we look at complex plots, sort of all these things, so we have this hue-like color function that we're using by default. It isn't quite hue. And so, for a comparison, if we try this, to use actual hue, and possibly I shouldn't have done it with the one that's got the resolution cranked up, then you see, well, I mean, the immediate thing you see is that it's shifted by half of its cycle. So it has sort of the reds and the blues reversed. But also this tends to just be a little bit too bright, and the result is that your eye is really attracted to some of the colors occasionally, like the yellows and the cyans and the magentas. And so we're actually using a new color scheme that we came up with, which is called balanced hue. And so you can use this in other places, and it's very similar to hue. It just has some of the brightnesses and saturations adjusted a bit so that things are, well, a little bit more balanced, and not quite such garish contrasts occasionally. And so now that we've sort of been introduced to our functions, and we've learned how to interpret complex plot and complex plot 3D, I'm going to now look a little bit at the second half of this page. Not all of these examples, but a few of my favorites. And so the first one is this one, which I always think of as what they taught you in school is wrong. And so when you're first learning algebra, there's various identities that they teach you, like log of a to the b is b times log of a. So in this concrete case, log of z squared is equal to 2 log of z. And it turns out that this is only true some of the time. It's only true sort of for when z has a positive real component. And so here we do a complex plot of our two, allegedly equal things over part of the complex plane. And what you see is that on the right half over here, everything matches up, perfectly. On the left half, they don't. There's actually a difference there. And so, I mean, this sort of thing actually comes up relatively frequently when people are working with a system like Mathematica, where the answer they expected to get isn't the answer they got. And it's because the answer that they expected to get, having done it by hand, is relying on an identity such as this that isn't globally true. So the other one is, again related sort of to powers, is that z to the a to the b is z to the b to the a, which is z to the a times b. And again, this is a thing where if I forget which two we did. So we did, right. I mean, so these aren't necessarily the same. There's, again, they're sort of equal for the right half of the complex plane, but you run into a branch cut on the left half for one of them, and I mean, in both cases, for negative imaginary components, that you run into differences. So that's one of my favorite examples. I mean, just because it makes it so obvious that this thing that you thought you knew isn't really entirely true. It's almost proof without words level of things. And then let's see, jump around a little bit. So this is plotting zeros of a function using complex list plot. And so if you have a polynomial of degree n, then you have n zeros, and if they have real coefficients, then things are going to come in complex conjugates, and if not, they can be wherever. But if you have zeros of something that isn't a polynomial, then you frequently end up with an infinite number of zeros or quite a lot of them. And so here we have some expression involving sine, and we're just looking at all of the zeros within a disk of radius 3. And you get, occasionally some really interesting patterns out of this. And similarly to that, we have this one, which is eigenvalues of random matrices, which ultimately comes down to zeros again, just in a slightly hidden form. And so if your random matrix is sort of suitably constructed with random real elements in the matrix, then what will happen is that the points will be uniformly distributed inside a disk. Well, for reals, it's uniformly distributed inside of half of a disk, because as I was saying, eigenvalues are really zeros, and random entries leads to random or to real valued coefficients, and so everything comes in complex conjugates, and so whatever's in the top half is in the bottom half as well. If you switch to complex numbers, then all the eigenvalues, in this case, end up being uniformly randomly distributed inside the disk, and you don't have the complex conjugates in this case. And so we're going to look at random 13 by 13 Frobenius matrices with integers whose entries are random integers from -1 to 1. And so we took a whole bunch of these, 100,000 it looks like, and we plotted the eigenvalues, and you sort of get this really cool fractal-like structure of where all the eigenvalues for these, this family of matrices live. And I think this was, sort of unexpected. I didn't come up with this example, so it was especially unexpected for me. I think the person who came up with the example may have been expecting some of this behavior. And So then, sort of coming back to and starting to touch on that manipulate that was shared earlier. So, here's that function, z squared plus c. This is, how you generate Mandelbrot sets. And so you keep applying this based on what your starting value of c is, it either blows out to infinity or converges. And so we can see those two behaviors right here. So this point is going to go out to infinity and never just keep going. These two are sort of converging slowly into a fixed value. If you choose your point carefully, you can get it to cycle. And so that's what this root object is here, is a very carefully chosen point, so that after every third point repeats itself, it just goes in a little triangle again and again and again. And so, and then the other thing that sort of occurred to me as a simple example of complex list plot is that we have this function called Mandelbrot set member Q that tells you if something is in the Mandelbrot set or not, whether that point converges or diverges under that iterated map. And so I just created 5,000 random complex numbers and grouped them according to whether they were in the set or not, and then threw it at complex list plot, and you sort of get a very pointillist representation of the Mandelbrot set. Not really great for seeing details along the edges, not surprising, but it's recognizable. And so that is, I think I'll stop about there. It's almost been an hour of us talking. We'll see if we have any questions, which it doesn't look like. We have. We'll double check to see complex list plot, how it's working in the cloud. So far as I know, it should work in the cloud. It's not doing anything really exotic.